Last video of Unit 9, Momentum and Impulse. Here we're going to look at some applications of the conservation of angular momentum. The external net torque on a system is 0. The formula for angular momentum, which is symbolized by L, is I, the rotational inertia, times omega, the angular speed, or velocity really, and the units are kilogram meter squared per second. What I want to look at here is whether or not it's possible for a particle to have angular momentum. We've already verified that extended bodies that rotate have angular momentum, but what if you have a particle? So let's go through the formula, I omega. Well, what are the different parts of this formula, and can they be applied to a particle? Starting from I, can a rotational inertia exist if you don't have an extended body? Absolutely. Yeah, we actually did this first when we first learned about rotational inertia. The rotational inertia of a single particle that moves in a circular path is given by mr squared. And that makes sense, right? Because essentially all of the mass that is rotating is at the edge, so it's the same as the inertia of a ring or a hoop or a loop. What about angular velocity? Can a particle have angular velocity? Absolutely. And there's even a relationship between its translational velocity and its angular velocity, which is V equals R omega. And if you wanted to, you could solve this for omega and say omega is translational velocity V divided by R, the radius of the circle. Learned back in Unit 5. So I told you about Kepler's laws, and we discussed how one of the laws, the second law specifically, says that in equal intervals of time, the area swept out by a planet that orbits the Sun is equal. In other words, even though the planet is not always the same distance from the Sun, it turns out that the planet, let me find my cursor here, here it is. It turns out that the planet moves faster here when it is closer to the Sun, and it moves slowest when it's farthest from the Sun, such that the blue triangle, sort of triangle that you see here, is always the same area. This is a direct consequence of the conservation of angular momentum. Since the gravitational force on an orbiting body is always radial, we can say that the angular momentum is conserved. Therefore, the only way it's possible for something's angular momentum to be conserved when its radius is changing is if its velocity is also changing. And that's shown here on the image on the right. So starting from this first vector, you see that the momentum mv is some length, right? This is maybe about an inch on my screen. And then this is visibly a longer vector down here at the bottom. And it makes sense because when you're closer to the Sun, you have a smaller r value, and you must therefore have a larger v value, and also because of v, a larger momentum value. This is Halley's Comet. This is a comet that comes around every 75.3 years, Earth years. And so it's only visible on average once in a human lifetime. Last time it was visible was in 1986. Next time you'll be able to see it is in 2061. So we're going to do some math with this because we can use angular momentum conservation. We're going to say first that the closest it ever comes to the sun, and this is true, and that's called perihelion, that's the word for closest approach of an orbiting body, is 0.586 AU. AU means astronomical unit, and that is the average distance that the Earth is from the sun. So this is an interesting result because this means that Halley's Comet, which right now is very, 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 very far from the sun, gets closer to the sun than we ever are. At that moment, when it's at its closest to the sun point in its path, its velocity is 60,000 meters per second. And then there's this other term, aphelion, which means what you probably think it means. It means the farthest away Halley's Comet ever gets from the sun, or really anything. Aphelion is how far the farthest anything is from its orbiting center. And that at its very, very farthest away distance, its velocity is 1,000 meters per second. This is now enough information for us to do something really interesting. On December 9th, 2023, Halley's Comet will reach its next aphelion, which means on that day, it will be the farthest away it ever is from the sun. And a cool result, I mean, if you think about what's going on there, that means that not only is Halley's Comet not yet returning to Earth or getting closer, it's going to be continuing to move farther away from the sun 8.5 years before it turns around and starts coming back. I want you to tell me then, how far away is the comet at aphelion? On December 9th, 2023, what is that maximum distance the comet will ever be from the sun? Now you should pause the video and try to use momentum conservation to solve this problem. Had a chance to solve here, I'm going to show you the answer. Since momentum is conserved, well, more accurately, angular momentum is conserved for all orbiting bodies, we can say that the angular momentum at perihelion, or the closest approach, is equal to the angular momentum at aphelion, the farthest away. And at these distances, it would be valid to model the comet as a particle. Its size is negligibly small with respect to how far away it is from the sun. So using the formula we introduced a few slides back, r mv sine theta equals r mv sine theta at these two moments. M is going to cancel out, and theta is the angle between the radial direction, or towards the sun, towards the force, and therefore the acceleration, and the velocity, and that's a 90-degree angle, or very, very close to it. And so sine of 90 is 1. We can drop out those sine thetas on both sides, and we say RV at perihelion equals RV at aphelion. Subbing in the values I gave, I'm going to leave the distance in terms of astronomical units. And all that means is that when I finish the problem, my answer will just be in astronomical units. I could convert that to meters, but I don't really need to unless I was asked to do so. So, solve it. You get 35 AUs, or in other words, at its farthest distance ever from the sun, which will next occur in 2023, we will say Halley's Comet is 35 times as far away from the sun as we are. Then it'll start coming back.